This first question is about copper. And if we look at the question and then do a little flow diagram, it helps to explain what's going on. So we've got copper 1 chloride. We can see it's copper 1 chloride because chlorine has an oxidation state of -1. And it's been dissolved in an excess of hydrochloric acid, and a concentrated solution containing this ion is formed, which is colourless. When we add hydrogen peroxide to an acidified solution, we form a green solution containing this complex ion X, and also water. And when we add water to this complex, we get a blue solution containing the copper complex Y. So first of all, the first part of the question is, what is the oxidation state of Cu in Cl2-? Well, the overall charge is minus, and if each chloride ion is minus, therefore the charge on the ion is equal to the sum of the oxidation states, and it's colourless, it must be +1. And the electron configuration of the Cu plus ion is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. It's lost its 4s electron. And we can see that it's colourless because it has a complete D or 3D subshell. And for a true transition metal ion to appear coloured, remember it has to have an incomplete D subshell so that the electron can be excited into a vacant orbital. Complex ion X, you can see there, this is the green colour when the copper 2 chloride, and remember we can only fit 4 chloride ions around it because they're quite large, and therefore because there are only 4 pairs of electrons repelling, the shape is tetrahedral. Now here the copper has got an oxidation state of +1 and it's gone to +2, so the hydrogen peroxide must be an oxidizing agent. Now we need to construct a half equation for the formation of water as the only product from hydrogen peroxide in acidic solution. So we've got H2O2 forming water, and whenever we've got oxygen, remember we always have to have, if we've got more oxygens on one side, we form water on the other side. There can't be any other product. So therefore we need 2 to balance out our oxygens. We've now got 4 hydrogen atoms on this side and 2 hydrogen atoms on this side, so we need to add 2 hydrogen ions to balance out for hydrogen atoms on this side. We now add electrons to the more positive side, so this side is 0, this side is plus 2, so we now need to add 2 electrons onto this side of the equation. Finally, write an equation for the formation of Y from X and identify the role of water in this reaction. So we have the tetrachloro copper 2. We're adding water molecules, and that substitutes the chloride ligands. We form the blue CuH2O6 complex, and all of the chloride ligands get substituted, and therefore the water is behaving as a ligand. First question is, what is the difference between a Lewis acid and a Bronsted-Lowry acid? Le lone pair acceptor. So we met this when we did organic chemistry, and our aluminium chloride in organic chemistry met as a Lewis acid. A Bronsted-Lowry acid is an H-stone. Now we know that aqueous ions, 3 ions, are very acidic in solution. So if we react aluminium chloride with water, we're going to form the F ion, and we're also chloride ions in excess. in order to balance this, we can see that we need to add 6 H2Os. Now this ion is very acidic because of the polarizing power, and therefore it can behave as a Bronsted-Lowry acid because one of the protons can react with water, which behaves as a base, takes off one of the protons, and therefore one of the waters is now left as a hydroxide ion. So there are now only 5 waters attached. Hydroxide ion has a negative charge, so that aqueous ion is a 2+ charge, and it's the H3O plus ion that causes the litmus to turn red. So it says, construct an equation to show aluminium chloride acting as a Lewis acid in its reaction with concentrated hydrochloric acid. So if we have AlCl3 plus HCl, it's going to accept a proton to form AlCl4 and H+. It's taken a lone pair of electrons from the chloride ion. Do what you would see when you add some iron 3 chloride, which is an orange solution, with an excess of sodium carbonate. Well, you can see here effervescence, and the ion containing product is formed here. So observation, we would write effervescence, and a orange brown precipitate. The formula of the ion containing product. Well, let's write an equation for that reaction again. Remember that the FeH2O6 is very acidic, and it's reacting with the carbonate ion. So to balance this, if we have 2 of these, 2 times +3 is +6, so we need 3 CO2s. Therefore, the ion containing product is FeH2O3OH3, which is a precipitate, and we're getting 3 CO2s and 3 H2Os. Now, it didn't ask for the balanced equation, but there is the ion containing species, iron 3 hydroxide. In this next question, it says aqueous chromium 3 sulfate is added to an excess of aqueous sodium hydroxide. Let's take a look at that. In this video, it's the other way around. So we add the sodium hydroxide, we get a precipitate. When there is an excess of the sodium hydroxide, the precipitate redissolves. Let's write an equation for that reaction before we give the formula of the chromium containing product. So bypassing the chromium hydroxide, there's the beginning species, the chromium 3 sulfate species. We add an excess of hydroxide, it redissolves in excess to give a charged ion. So the formula of the chromium containing product is Cr. You've still got your 2 waters left, but 4 of the waters have lost their protons, so we now have 4 hydroxide ions, and the overall charge is negative. Some textbooks you might see CrOH6, but this makes more sense. A substitution reaction is simply the substitution of one ligand for another. Clearly, all that's happened here is 2 of the chloride ligands have been substituted by 2 water molecules, and therefore the 2 chloride ligands will appear on the other side. Notice the charge should balance on both sides. Overall charge on this side is +1. Overall charge on this side is +1. What change to the titanium ion is responsible for the colour change in the reaction? It's simply the ligand substitution and not a change in oxidation state. We're going to walk through this and add annotations as we go through it. So we have a crystalline solid A, which dissolves in water to give a metal complex B. So immediately we can write our metal complex as MH2O6. We don't know the charge on it, so I'm just going to put Sx+. When we add silver nitrate, we get a white precipitate of C. And we know that silver ions react with chloride ions to give a white precipitate. And the white precipitate must therefore be AgCl. We'll call that C. This dissolves in an excess of dilute ammonia, and when dilute ammonia is added to silver chloride, it forms the ammonia complex, which is linear because 2 ammonia molecules donate a pair of electrons each. That's NH3. Let's start that again. That's NH3 2, and the overall charge is plus because it's a silver plus ion, and the chloride ion is left in solution. The solution of A becomes blue, containing metal complex E, when excess of concentrated hydrochloric acid is added. We know that the only complex that is blue when concentrated hydrochloric acid is added is this one here. That is pink cobalt going to this beautiful blue cobalt solution here. Let's fill in our answers so far. So we have identified our precipitate of C, which was silver chloride solid, and we know that the formula of the complex ion D is the diamino silver with a positive charge. We know the complex ion E is our beautiful cobalt Cl4. Remember 4 chlorides usually because you can't fit 6 around. The overall charge is 2 minus because it's cobalt plus 2. Now it then tells us that concentrated ammonia is added to a solution of A. So we now know that A had to, complex ion B had to be the beautiful pink COH2O6 2 plus. So now we said we're adding aqueous ammonia to our COH2O6 2 plus, and we form a blue-green precipitate. So here's our concentrated ammonia and our blue-green precipitate, and then it's added in excess, and we can see that when it's added in excess and left to stand, it goes brown, and when we leave it to stand in air, so we get a brown solution, when it's left to stand in the air, it goes darker at the top. Let's write an equation for the formula of precipitate F before we deduce its formula. So that's COH2O6 2 plus. We then add some ammonia solution, and initially the ammonia behaves as a base because we see a precipitate, and therefore the base has to be, the blue-green precipitate has to be, let's change the colour, blue-green precipitate has to be the COH2O4 OH. It's got no charge anymore, it's lost its 2 plus charge, and therefore it precipitates to form the cobalt 2 hydroxide, and the ammonia molecules form ammonium ions. This then dissolves in excess to give a brown solution, which is complex ion G. So the complex ion G is when we have ligand substitution and the waters are removed and ammonia replaces each of the water ligands, and we get 6 of these surrounding it, and that is the complex ion G, which is brown. Now on standing, certainly near the top of the test tube, it goes an even darker brown, and that is the cobalt 2 is now oxidized to cobalt, put H2O in there, the cobalt is now oxidized to from cobalt 2 to cobalt 3 plus. The starting solid must have therefore been cobalt 2, so the metal ion is cobalt, and chloride ions were present, and therefore because it's cobalt 2 it must have been CoCl2, CoCl2 solid. First question is AS revision. What is a coordinate bond? And we know that's the sharing of a pair of electrons both donated from one atom. We've met this question earlier, so I'm not going to fill it in. Bronsted Lowry acid is a proton donor and a Lewis acid is a lone pair acceptor. What is meant by a bidentate ligand? So that is a species which can form two coordinate bonds or which can donate two pairs of electrons to a metal ion. State how the coordination number of cobalt-2 ions in an aqueous solution changes when an excess of chloride ions is added. Well, let's just remind ourselves from the last question. We have CO, H2O6 are the cobalt species in water, but when we add chloride ions, the coordination number changes from 6 to 4 as we form the blue CO Cl4 2- and the 6 water molecules are substituted. And the reason for the change is there is greater repulsion between the larger chloride ions. Suggest why the enthalpy change for a following reaction is close to 0. Well, remember, enthalpy change is the sum of the bonds broken minus the sum of the bonds made. So the number of bonds broken, or the type of bonds broken, equals the bonds made. So here we have broken 6 coordinate bonds and we've formed 6 coordinate bonds, even though these are bidentate ligands. Remember, ethane 1,2-diamine can be, if we draw the structure, so we let the examiner know we know the structure of ethane 1,2-diamine, and we put our lone pairs on and we can label that as En. So the formula of the compound, when ethane 1,2-diamine is treated with an excess of hydrochloric acid, this simply behaves as a Lewis base and accepts a pair of protons, and we simply get the salt. So if we look at the next passage, it says iron 3 nitrate monohydrate, very pale violet colour. It contains the FeH2O6 3+ ions. Now when you add this to water, they dissolve to form a brown solution. And this brown solution with conc nitric acid yields a very pale violet solution. So any ion which has got 6 ligands is going to be octahedral. Write an equation for the FeH2O6 ion behaving as an acid in water, in aqueous solution. So because it's highly polarizing, the central Fe3+ ion, it behaves as an acid and it donates a proton to the water, and therefore this loses a proton, so it's left as FeH2O5 OH 2+, because it's lost of hydrogen. The water's picked up the hydrogen ion. Deduce the formula of the species responsible for the brown colour of the solution. Well, the brown colour is due to this more common species here, and this colour, and this rarer species is violet. So this is the brown orange colour that you're used to seeing in iron 3 solutions. When you add very concentrated nitric acid is a very strong acid, and therefore it must force a proton onto the brown solution here and forces it to accept a proton to form the violet FeH2O 5 at 6 3+ ion. This next question could relate to any transition metal ion. So you always get a colour change whenever you change the ligand or you change the coordination number. Now we can't have changed the oxidation state because iron 3 is the highest oxidation state. So quite simply, there has been a change of ligand and a change in coordination number, because it's gone from 6 to 4, and a change in coordination number. Next question. When excessive magnesium metal is added to iron 3 nitrate, effervescence occurs. Well, whenever we add metal to an acid, we always get hydrogen gas evolved. To deduce the formula of the precipitate, let's now write an equation for the reaction. So we have our acidic FeH2O6, which is very acidic, 3 plus iron, reacting with magnesium metal, and we're going to form FeH2O because it's going to lose 3 protons, OH3. That's the precipitate because it's got no overall charge as a solid. Hydrogen gas has been evolved. Now, in order to make the hydrogen gas, the magnesium needs to lose 2 electrons to form Mg2 plus Aq. Again, this is very similar to the carbonate. If we have 2 of these, that will release 6 protons altogether, and therefore that will release 3 hydrogens. Therefore, you're going to need 3 magnesiums, which are the reducing agent, to form 3 hydrogens, and you're going to form 3 magnesiums and 2 moles of the hydroxide. Next question, dead easy. Complete the electron arrangement of the cobalt ion. Go to periodic table and you will find that cobalt is 3d7 4s2. So it will lose its 4s electrons and its remaining electron configuration will be 3d7. Give the formula of the complex present when an aqueous solution of cobalt sulfate and state is colour. Well, we know that all hexaaqua cobalt is pink. So it's COH2O6 2+. The colour of the complex is pink. We've already seen the video to the reaction of the cobalt complex. So when we react it with an excess of aqueous ammonia, we form a new complex which is brown, and I'll just change that to a nice brown, slushy brown colour. There we go. So the formula of the new complex is CONH3 6 2+. The colour of the new complex is brown. So to write an equation for the formation of that complex, we've got the pink cobalt, which is COH2O6 3+. It's a ligand substitution, so we need 6 NH3s, and that reacts to form the CONH3 6 2+. Now when we add hydrogen peroxide to this mixture, the colour of it darkens due to the formation of a different complex, and we know hydrogen peroxide is an oxidizing agent. The same will happen in air. It will rapidly oxidize to CONH3 6 3+, which is a dark brown colour. Here's a nice reaction sequence with ammonia. So let's walk through it and annotate it. So whenever we add water to copper ions, we know that the formula of the complex is CuH2O6 2+. When we add a few drops of ammonia, the ammonia behaves as a base and removes 2 protons. So the pale blue precipitate is CuH2O4 lost 2 protons, OH2, which precipitates out. When you add an excess of ammonia, then a ligand substitution takes place and we get a much darker complex, and the formula of that is CuH2O2. We can never remove 2 of the waters. 4 of the waters are substituted with ammonia molecules, and the overall charge on that is 2+, and that's a deep blue solution. Let's remind ourselves of that reaction. So the blue solution is this species here. We've added some dilute ammonia to get that precipitate. So the ammonia behaves as a base and removes 2 protons. When we then add an excess of the ammonia, it redissolves to form this deep blue complex, this deep blue solution, which is this complex here. We can never substitute 2 of the water molecules, so we just have 4 of the ammonia molecules carrying out the ligand substitution reaction. So this is some AS revision on oxidation states. We know that the nitrate ion has an overall charge of -1 and the oxidation state of nitrogen is +5. In NO2 it's +4. The only oxidation product can be oxygen because it was -2 in the NO3, and copper can't be oxidised because it's already in its highest oxidation state. Finally, the copper containing species in solution A we've already identified as our CuH2O6 2+, and the shape, because it's got 6 coordinate bonds, is octahedral. The pale blue precipitate can't be anything else, the hydroxide. So the Cu, 3 waters are left on, 3 protons are gone, it's got no overall charge. The equation for the reaction with ammonia is behaving as a base. So the CuH2O6 loses 2 protons to lose its 2+ charge, and therefore it needs 2 ammonias to remove those protons. The ammonia is behaving as a base. So it forms CuH2O3OH2, and the ammonia becomes ammonium ions. Finally, identify the copper-containing species in solution C. So C was when that dissolved in excess ammonia, so that's CuH2O2 NH3 2+. The colour is deep blue solution, and forming it from the precipitate, so our precipitate is CuH2O4OH2 solid, and we now are going to replace the hydroxides and 2 of the waters with 4 ammonias. So the deep blue solution is CuH2O2 NH3 2+, and therefore we've kicked out 2 waters, and we've also kicked out 2 hydroxide ions. Identify the copper containing species in solution D. Let's remind ourselves what happens when we add concentrated hydrochloric acid to that blue solution. It starts to go green, and there is the colour of the final complex. So it's tetrachloro, because we can only fit 4 chloride ions because of their size and repulsion. The colour is green and the shape of the complex is tetrahedral. The oxidation state in this complex is +1. Give the electron configuration with copper ion in +1. We've done this before, it's 3d10. Deduce the role of the copper metal in the formation of CuCl4 3- from the copper containing species in solution D. So let's have a look at our reaction sequence again. Well, obviously this has got an oxidation state of +2, and that's +1. It has been reduced. So the behaviour of this is a reducing agent. The copper